Chapter 6, Chemical Equilibrium. Section 6.6, Le Chateliers Principle. When the reaction quotient Q is smaller than the equilibrium constant K, the reaction proceeds forward to increase Q until Q is equal to K. When Q is greater than K, the reaction proceeds backward to reduce Q until Q is equal to K. And these two statements are the basis of Le Chateliers Principle. In plain words, when Q is greater than K, the system is overreacting. It would like to go backward until the equilibrium is reached. When Q is less than K, the system is underreacting, so it's going to move forward to increase Q until Q is equal to K. When Q is equal to K, the reaction proceeds in neither direction. The reaction system is at equilibrium. When a reaction or physical change is at equilibrium, we have this equation, Q is equal to K. There are two different ways to break the equilibrium or to break this equation. You can change Q, you can change K to break this equilibrium. Changing the reaction temperature may change the equilibrium constant of a reaction in the standard state or actually any other states. But now let's look at the standard state first. This delta G of R in the standard state is equal to negative RT times the natural logarithm of K. And now look at this equation. We just need to divide both sides by negative RT. We get this. And G is H minus Ts, so we have delta H minus T delta S. Note we have a specific temperature right here. That's why we can take T out. Now we can rewrite this to be negative delta H over RT plus delta S over R. And again, we have this standard state superscript. And now we have this equation, L and K is equal to negative standard enthalpy of reaction over R times 1 over T plus the standard entropy of reaction over R. This is considered a linear equation. And why is that? The natural logarithm of K, this is your Y, 1 over T, that's your X. And over here, negative enthalpy, standard enthalpy of reaction over R, that's the whole thing is the slope. And over here, delta S over R, that's the intercept. So we can see this equation can be plotted in a Excel graph if you do L and K as the vertical axis and 1 over T as the horizontal axis. And you will be able to get the slope and the intercept simultaneously with a linear regression. The temperature dependence of the standard enthalpy of reaction and the standard entropy of reaction is often negligible within a small or even moderate temperature range. This is just because the integral of delta CPM is small compared to the standard enthalpy of reaction. The integral of delta CPM over temperature dt is relatively small compared to the standard entropy of reaction at room temperature. So that's why we can just plot this L and K versus 1 over T. It's approximately a linear plot, and we get the slope. The slope is negative standard enthalpy of reaction over R, and we can get the intercept. The intercept is simply the standard entropy of reaction over R. Given the values of the equilibrium constants at 2 or more different temperatures, we'll just graph this L and K versus 1 over T, and we'll be able to get the slope. And the standard enthalpy of reaction is negative R times the slope. The standard entropy of reaction is the intercept times R. So again, we have this equation. The natural logarithm of equilibrium constant at a given temperature is negative standard enthalpy of reaction over RT plus the standard entropy of reaction over R. If we have an endothermic reaction, this standard enthalpy of reaction is positive. And then therefore this slope should be negative. Why? The slope is negative positive number over R, that's negative. Therefore, as the reaction temperature T increases, 1 over T decreases, and if 1 over T decreases, L and K increases, K increases. So in this situation, for endothermic reactions, When temperature increases, the equilibrium constant increases. However, for exothermic reactions, everything's backward. This enthalpy of reaction is negative, and this ln(k) versus 1 over t slope is positive. And when temperature goes up, 1 over t decreases, and therefore k decreases. Again, for endothermic reactions, when you increase the temperature, the equilibrium constant increases. For exothermic reactions, if you increase temperature, the equilibrium constant decreases. Again, k increases as t increases. For an endothermic reaction, the reaction will proceed forward to reduce the temperature change. K decreases as temperature increases. For a exothermic reaction, the reaction will proceed backward to reduce the temperature change. And again, this is just a part of the Le Chatelier's principle, and also the most important part of the Le Chatelier principle. Now let's look at these two graphs, one for endothermic reactions, one for exothermic reactions. For endothermic reactions, the standard enthalpy of reaction is positive, and then the slope is negative. A standard enthalpy of reaction over R, so the slope should be negative. So you see this line pointing down, and the y-intercept is the standard entropy of reaction over R. So again, this is just we're plotting this ln(k) versus 1 over t. This is how we determine the slope. And now exothermic reaction, pay attention to the difference. Now this line is going up. This is because the standard enthalpy of reaction is negative, and we have one additional negative sign in front. So the slope is positive. While the slope is positive, the standard enthalpy of reaction is negative. And again, the y-intercept is the standard entropy of reaction over R. So if somehow you can determine the slope and the y-intercept, you will be able to determine the standard enthalpy of reaction and the standard entropy of reaction at the same time. Now again, let's look at this reaction. This reaction is ln(k) is equal to negative standard enthalpy of reaction over RT plus the standard entropy of reaction over R. When the endothermic reaction is at equilibrium, increasing the reaction temperature may result in Q less than K, because that will just increase K. So it's going to break this equilibrium. K is now greater than Q. Therefore, the reaction should proceed forward, and that will absorb heat. When it absorbs heat, that will reduce the temperature. That's just the prediction of Le Chatelier. And now for a exothermic reaction at equilibrium, Q is equal to K. Now increasing the reaction temperature will reduce the value of K, and in that case now Q is greater than K. The system is considered overreacting. The reaction should proceed backward so that Q is equal to K again. What if the standard enthalpy of reaction is 0? This is rare, but if it happens, well, then if you look at the slope is simply 0, because the standard enthalpy of reaction is 0. That means this K does not depend on temperature at all. So for such a reaction, well, when it's at equilibrium, if you change the temperature, it's not going to disturb the equilibrium, because you're not changing Q, you're not changing K either. K does not depend on temperature. Le Chatelier principle states that when change is imposed on system at equilibrium, the system will respond in a way to counteract the change. That's the essence of the Le Chatelier principle. This principle suggests that after an endothermic or exothermic reaction reaches equilibrium, increasing the temperature will shift the reaction either forward or backward to absorb the heat and to reduce the temperature. Le Chatelier's principle applies to phase changes as well. If you increase the temperature of the liquid-gas mixture of the same substance, it's going to shift the equilibrium towards the gas side, because when liquid is converted to gas, it's going to absorb heat. That will reduce the temperature, and that will result in a higher gas pressure. What if you want to do a more quantitative analysis for the vaporization from a liquid to a gas? Well, we can use this equation. The natural logarithm of K is defined to be ln P over 1. P is your product. That's the partial pressure of the gas. One is for the pure liquid. This is a mole fraction of this pure liquid. It's equal to negative. Now the reaction is vaporization, so we have negative delta enthalpy of vaporization over RT plus the entropy of vaporization over R at this given temperature. Again, if you increase the temperature, this system will convert liquid to gas to absorb this heat to bring the temperature down. If you lower the temperature, gas is converted to liquid and release heat that will bring the temperature back up. When the quotient of reaction is equal to its equilibrium constant, that means the reaction is right at its equilibrium. In short, we have Q is equal to K at when the reaction is at equilibrium. We can also change the value of Q to break the equilibrium. For example, if we have this reaction that involves only gases, we have this expression, Q sub P, the reaction quotient of pressures. We have products on top, reactants on the bottom. Now we can actually compress the reaction system to increase the partial pressures of all gases by the same factor tau. And if it's compression, tau is greater than 1 because all those 4 species will have a larger partial pressure when the system is compressed. Now we have a new reaction quotient, Q sub P prime. Q sub P prime is equal to Q sub P times this tau to the power of delta nu. Delta nu is the change of the coefficients. So sometimes we have delta nu less than 0. That means, well, we have more gases on the left, less gases on the right. And then compressing the system will reduce Q sub P. Because if you look at this tau is greater than 1 for compression, delta nu is less than 0, so this factor is less than 1. And that means this new Q sub P is less than the original Q sub P. And now this new Q sub P is now less than the equilibrium constant. That means the reaction should proceed forward, which results in the less amount of gases when the system is compressed. What if delta nu is greater than 0? Then compressing the system would increase the reaction quotient because tau to the power of delta nu in this case is greater than 1. Again, compression, so tau is greater than 1 and delta nu is greater than 0, and then we have tau to the power of delta nu greater than 1. This reaction quotient will be greater when the system is compressed. QP prime is equal to QP times tau to the power of delta nu, and this tau to the power of delta nu is greater than 1. So the new reaction quotient QP prime is greater than K. The system is overreacting. That means the reaction will proceed backward, which would result in again less amount of gases to counter the pressure increase caused by the compression. So if you compress the system, the pressure goes up and the reaction should proceed in a way to actually reduce the amount of gases to bring the pressure back down. Again, that's just the essence of the Le Chatelier's principle. The system responds in a way to reduce the change either in temperature or in pressure. Now, when a reaction is at equilibrium, Q is equal to K, we can change Q to break the equilibrium. Again, we have this equation for the reaction quotient of pressures. There is a way to just change the partial pressures of all species. For example, if you compress the system, the partial pressures of all 4 species would increase. If you expand the system, the partial pressures of all 4 species will decrease. Now, what if we introduce more products in the system? So once the reaction system is at equilibrium, we can introduce more X or more Y in the reaction system. And then in that case, the new reaction quotient QP prime will become larger than K. So for example, when the reaction is at equilibrium, Q is equal to K, so we have all this. Now we just introduce X, we put more X in the system. this p sub x increases, and then we'll get a new reaction quotient, and this new reaction quotient is larger than the previous one, and it's also larger than k, and that means the reaction will proceed backward. What if we introduce more reactants in the system? So if we add more A in the system, all right, over here, that means the new reaction quotient is going to be less than K. When that's the case, the reaction should proceed forward. So again, that's the essence. If you are adding reactants, well, the reaction should proceed in a way to consume the reactant. If you are adding the products, the reaction should proceed backward to consume the product. What if we introduce some spectators? Well, it depends. If we introduce helium gas in the system on a constant volume condition, actually that has no effect on the partial pressures of any chemical involved in this reaction. Therefore, it has no impact on the reaction quotient. Again, if it's constant volume condition, you introduce helium gas as a spectator gas, it's not going to affect the value of Q sub P. Therefore, you're not going to break the equilibrium of this reaction system. There's not going to be any change. However, if you introduce spectators in the system under constant pressure condition, so this is tricky. Although I did say constant pressure condition, well, if you look at the final state of the system after the introduction of helium, this P actually includes the partial pressure of helium and then partial pressures of X, Y, A, and B. So although the total system pressure is constant, the pressure of the reaction system is reduced. That means the sum of the partial pressures of X, Y, A, and B, well, is reduced. That's equivalent to the expansion of the system. Again, this is equivalent to the expansion of the system because the partial pressures of X, Y, and B are all reduced by the same factor after you introduce this helium gas under the constant pressure condition. Again, before you introduce this helium gas, we have a total pressure P for the entire system. After you introduce this helium, all right, the partial pressure of helium plus the total pressure of this reaction system is P. So actually this P minus the partial pressure of helium is now the actual sum of the partial pressures of the reaction system. So this is equivalent to the reduction of the pressure of the reaction system. And then this reaction should proceed in a way to increase the pressure of the system excluding helium. All right, so if delta nu is greater than 0, that means we have more gases on the right hand side, then the reaction should proceed forward. When delta nu is less than 0, that means we have more gases on the reactant side. So in that situation, the reaction will proceed backward to bring up the sum of the partial pressures of X, Y, and A and B. All right, and that's also based on the essence of the Chateliers principle.